it's my pleasure to welcome Professor Bernd Büchner, who is director of IFW Dresden and who is the main responsible for this project. It was his initiative from very beginning, from Ukratop, and I welcome Bernd, please.
Okay. Thank you very much, Sasha. So I will try to share my screen now. So it's also, I should emphasize that this project, this new project, which we are now starting, does it work?
Yeah, it's working. If you make it on the full screen, it will be a bit better.
I'll do my very best. Let's do it like that. Okay. So that this project...
Now it's not full screen. It's just what you see on different monitor, probably. You can switch.
Let's do something like
presentation mode.
Now?
Now it's perfect. Yeah.
That's better. So that this project, let's go back. Oh, no, sorry. So this project, which we start now, it's also very, very important for us. And I think it's a continuation of a big success story. And thank you very much that you give me the opportunity to be the first speaker here. Actually, I was asked not to give a scientific talk, but to give an overview over the institute and over the project. And I'm I'm happy to do that. We'll discuss a little bit the scientific cooperation between Ukrainian scientists and us at the IFW Dresden. So introducing this German-Ukrainian Research Center for Quantum Materials. And here you see a picture from our entrance where some of the Ukrainian guests were presenting some flags from Ukraine some time ago. So this doesn't work. Why doesn't this work? Okay, let's do it like that. Let me first start with introducing our institute. So the name of our institute, so IFW Dresden, stands for Leibniz Institute for Solid State and Materials Research in Dresden. And we can go through this name. So what does it mean, Leibniz Institute? That means we are one of the institutes put together in the so-called Leibniz Association. Leibniz Association is an association of non-university institutes. Nearly 100 of these Leibniz institutes are present all over Germany. They are independent institutes. This is non-university institutes. They cover a very broad range of topics from social science, economy, but also natural science. And we are one of the only institutes, I would say, where physics or fundamental physics also plays a role. But in general, all these Leibniz institutes follow the agenda from theory to applications. So theoria cum praxis, that's, let's say, a general theme of all these Leibniz institutes. But the rest, we are rather independent and loosely connected in these Leibniz association. So what we are doing is we are doing solid state research. So we are doing fundamental science from theory, experiment, and synthesis on all kinds of condensed matters. But we also try to go a step further from these fundamentals to something which is called materials research. So where we really try to also get some technology development or some material science, not only condensed matter physics, but also material science in the sense of materials engineering is a part of our story. It's also in our name. Okay, and we are located in Dresden. This is a picture from Dresden. It's an old city, let's call it like that. There's a lot of Baroque in there, old churches, there's a Frauenkirche. So, but we also have a lot of high-tech meanwhile in Dresden. There are many companies, many research institutes, a large university, one of the excellence universities located here in Dresden. And that's also should emphasize, we have a really Ukrainian community now. This number is given by the city. So there are about 8,000 Ukrainian people here around. So let's see, if you come here, you can also speak Ukrainian. So what we are doing is, and that's our slogan, we are working on materials for technologies of tomorrow and beyond. And for us, it's quite important that, okay, on the one hand, it's clear we are working on materials. That's the common theme of our research at the IFW. We have technologies in our mind, but it's important for us to state that this is not technologies of today, but also of tomorrow and beyond. That means we are also trying to explore really new concepts for technologies, materials which are promising for future technologies, which are not even cannot even be foreseen at the moment. And this materials-oriented research and development we do in 5 disciplines, from theoretical condensed matter physics, experimental condensed matter physics, chemistry, materials engineering. So this is now these 2 engineering parts, where we have materials science and materials engineering and electrical engineering, both disciplines. And here are just some examples showing you the broad spectrum from skyrmions, which are also very much relevant for QMatS. This we will learn more on platinum bismuth later on. So it's a superconductor and topological material, but also some steel is studied here. Thermoelectric coolers or solar cells, all this whole range relevant for condensed matter of material science. So again, we are organized so we have 5 disciplines, and we are organized in 5 so-called IFW institutes with directors. These directors are jointly appointed at the university. So we always have both this non-university character in the IFW, but simultaneously the professors are at the university, which is very much relevant, for example, for all kinds of teaching activities, for PhD thesis, for supervising master students. This can also be done directly with the university, since the directors are simultaneously full professors at the university. So I myself, I stand for the Institute for Solid State Research. I'm located at the Faculty of Physics, and we are working on experimental condensed matter physics in our institute mainly. Cornelius Niersch, the second director, is working in the Institute for Metallic Materials. He's associated with the Faculty of Engineering, Materials Engineering. Our new colleague Anjana Devi, she's working on materials chemistry, connected to the chemical Faculty for Chemistry in Dresden. Jana is also rather recent professor, Jana Weinshoff. She's associated with the Faculty of Electrical Engineering. And last but not least, Jeroen, who will give the next talk, and he's also associated with the Faculty of Physics, but he's working on theoretical condensed matter physics. And then we have 2 W2 professors, also both. There's Axel Lupp, working on TEM techniques, again, also Faculty of Physics, and Julia Hufenbach, she's professor at the other university, nearby university, which is very strong in these materials, metallic materials or materials engineering, and there she's a professor. Okay, this is our team of the directors and professors. The resources of the institute, we have about 500 or 560 people working here, 250 scientists. Out of these 560, we have a lot of PhD students. You see, teaching is a large activity, so we have 140 PhD candidates, including visitors, but we have also master students and bachelor students working here in the institute. So the total budget is about 47 million euro at the moment. So it's about the largest part comes directly from the federal and state governments. One has to emphasize that this is not only money which you can use for research. So for example, you have the buildings, and we have all this administration and all these things. You have to cover that. So this is the total money. These 12 million is the money which you get from project grants, either from European Union or from DFG, so from German Research Association, and also from the BMBF, where also our joint project is funded. So this is the budget and the infrastructure. So we have about 30,000 square meters lab and office space. We are directly located at the university, which is a big advantage. So that means we can do lectures here, and also for students, they can really join the lectures at the university. There's a very strong contact to the faculties. And we are, on the other hand, rather well equipped with all kinds of infrastructure which you need for materials research, starting from crystal growth and thin film growth, clean room. We have a large clean room, and then we have a lot of spectroscopy and methods to characterize the materials. Our research, we are studying phenomena and functions that occur at the level of electrons, atoms, and molecules, or nanostructure. And what we want to do is we want to understand the materials, want to calculate or even predict the properties of materials. So this basic research is a part of our study. It's of course connected to theoretical physics. We are developing methods to understand the materials. We do not only use methods, but we also develop methods to understand materials. And then finally, we also ask ourselves whether we can modify, we can optimize the materials to induce new functionalities or even applications. And we have this triangle here discussing our main aspects, and you see these quantum materials, which is of course also important for our joint activity is mentioned here. We also do that on nanoscale materials, and we have in mind the function and maybe also sustainability of these materials. A little bit more detail, we have this research area, and these are these functional quantum materials. So we try to get new functions due to novel, unconventional electronic properties. So superconductivity, magnetism are the prime examples. Topology also is maybe a new, more modern aspect which fits to this whole activities. And then we have activity which is more located on nanoscale objects, where the function comes through size, so that the properties and functions result from really structural arrangements or nanoscale aspects which are then relevant. We combine nano and function in this research area 3, where we address quantum effects at the nanoscale. Of course, if you want to go to apply quantum materials, you typically have to have some devices. You have to have this nanoscale aspect as well. And then we have a research area 4, which is more towards applications, where we really try to improve, for example, photovoltaic technologies, sustainable electronics, and similar things. So these are the research areas. And in the next minutes, I will show you some highlights from recent work. And the first one is this work on platinum bismuth 2, which will be later discussed in more detail. That's a beautiful, nice example because it's an interaction between these disciplines. So crystals of platinum bismuth as a two-dimensional material are synthesized here in the institute. They are experimentally studied in detail, for example, by photoemission, as you will later on show spectacular properties. And there's a close connection to theory, where the theoretical calculations or even predictions are made. So theory, chemistry, and experimental physics come together and try to do nice joint work. Actually, this nice work has been published in Nature recently, but it's not only a nice example of the joint activities within the IFW, bridging these 5 disciplines which we have. It's also a nice example for interaction between Ukrainian scientists and Germany, since our first author is Andrei. He was an UCA top student here and is now close to finalizing his PhD work. And then there are 2 other guys which have Ukrainian background, let's call it like that. And we are also participating in this. This is an activity which was basically driven by the experimental physics. So the idea of having really new properties like the superconductivity in topological material. This is another example. And here the idea came from theory. And it's also very recent work. It's also related to Ukrainian PhD student here. It's the first demonstration of a non-emission topology in a condensed matter system. And that's, you see this multi-terminal thing. And what you measure here is a transport property. And what you mimic with this device is really an Hamiltonian, which has been derived in the theory. So it's, let's say, an experimental realization of a non-emission Hamilton operator, Hamiltonian. So, and then you can really study this thing. You can compare to theory, but what you can also do, we can go a step further. You can really drive this to applications, and there is a patent application is pending, and there are a lot of activities now going in this direction. And QL is really very important in this activity as well. I'll give you some other example. This is also a rather recent activity, and this is you see in material, interesting material is a layered material. It's also an intrinsic van der Waals material, but in this case, a complicated one. But what you see here is, on the one hand, it contains manganese. That means a material which has spins, and so you have layers here which are magnetically ordered, actually ferromagnetically ordered. And then in between, you have layers of bismuth telluride. Bismuth telluride is known as one of the famous examples of a topological material. And so you have a connection between magnetism and topology. And this is very promising. There are clear predictions that there should be surface states which are protected, which can be used for spin transport. And okay, this work has been attracted a lot of attention. Here in this case, it was initiated by chemistry, I would say. So chemists, we were able to grow this for the first time. That was Anna Isayeva at that time. Then there was a big team with experimental theoreticians again. And then there was a lot of following works studying this material. Another example, also closely connected to activities which might be relevant for our consortium. This is now from Nikola Poch's team, from Cornelius Niel's team. What he's working on are some heterostructures which are formed by twisting superconductors. And the starting material is this BISCO. This is one of the cuprates, where again we have this van der Waals bonding in the bismuth layers. You can exfoliate it and can twist it and put it on top of each other again. And you end up with some Josephson junctions, which then, of course, the properties of these Josephson junctions depend crucially on this twist angle. And this is, let's say, also an ongoing activity for both studying the basic properties of such Josephson junctions, but also there are ideas to generate some kind of functionality, some kind of devices in this direction. Next example is again van der Waals material, which is often studied here. These are, you see again, these 2D materials. In this case, these are materials which contain iron and nickel. So they are again magnets, and they are 2D materials. And what has been done in these two papers was the study of their electronic properties, trying to understand their general characteristics, whether it's a Mott insulator, or what is the origin of the magnetism here. And of course, again, the idea is then to exfoliate these materials, to go down to monolayers, to manipulate the magnetism, to connect these magnetic 2D materials, 2D materials to superconducting or topological things. So this is just the idea using this van der Waals text to do devices and physics. Sorry, I continue. That's another example, very much relevant for work in our consortium. This is now work based on our TEM expertise. As Axel Luppes is crucial here at that point. And what they studied here is really the magnetic profiles in such curved nanostructures. And I think it's correct to say that we have perfect methods, TEM-based methods, to study really the 3D magnetic textures in all kinds of materials. You can measure 3D texture of fermions, and you can investigate them in very much detail. Another example from 2D materials. In this case, it's again chemistry driven. You see the new material here, where you have this typical motif of 2D materials, but here the top and the bottom layer are different, and therefore these materials are called Janus materials, have been grown here in Silke Hampel's team, published in a chemistry journal, and now the physicists start to investigate this material, look whether there are really interesting new properties originating from this fact that we have, let's say, a different version of a 2D material. Okay, this is already mentioned earlier, perovskites, solar cells, as Jana Weinshoff mainly working on there. She's very active, very successful, very visible in optimizing the performance of these new materials, these new photovoltaic materials. First demonstration of solar cells based on formation of phase heterojunction was the main topic of this recent paper. Okay. So there were a lot of examples of recent work. So we have a lot of ongoing research activities. We have these research fields based on quantum systems and based on nanoscale materials. But we also have a lot of, I would say, unique high-end methods. And this is just one example. Also, we developed these methods, so-called high-resolution yields machinery. It's TEM-based, so it's connected to Axel Lupp. Axel professorship is paid by a company, so this is a company which really is dealing with optimizing such objects like the monochromators or filters here. And together with the company, we are developing this spectrometer. It's at the end of the day looks like a usual electron microscope, but in situ there are monochromators. There's a special sample space which allows cooling down to helium temperature, and there's an energy filter which allows to measure with extremely high resolution the energy of the electrons. And what you can do that, having a monochromized electrons and having a nice energy filter here, you can measure the energy loss of electrons when they pass the sample to the sample. And this means you can do spectroscopy. You can do spectroscopy of excitons, plasmons, and all kind of other excitations. And this you can do now spatially resolved, so with sub-nanometer resolution in principle. Maybe not for the highest resolution, energy resolution, but of course, you have TEMS, we have sub-nanometer resolution, spatial resolution, and you have a momentum resolution. So you can also measure the excitations as a function of Q. And that's something unique. If you combine this together with the low temperature, then it's a unique method which is currently developed here at the IFW. And the first experiments are running now, first papers appear, and but we are still improving the energy resolution. There's another example far away from this basic science. This is really applied science, the surface acoustic waves. So we have two groups actually working on such applications based on acoustic waves like this, which can be controlled by electrical fields. Of course, in piezo materials, you can do that. Using this technique, you can create sensors, you can create telecommunication components. So most of our modern handies actually use patterns which have been derived together with industry here at the IFW for filtering frequencies. At the moment, we are mainly focusing really on sensors, for example, for wind turbines, get information on the ice formation or even clean the wind turbines from ice if necessary. We can do high temperature sensors. So there's a lot of activity ongoing in applications, and this is connected in this SAW lab Saxony. That brings me to these patterns. So we have a lot of publications. You saw all these Nature articles, which I've shown you earlier, but we also have a lot of patents here in many, many different directions. So at the moment, it's about 67 patents we have in Germany, also international patents. So roughly, we have about 5 to 10 patents applications every year. And these patents are important also for industrial corporations. So for example, we have the licensing of the DFT code, the FPLO, which got basically theory code, which is licensed. But it's also, of course, connected to spin-offs. So we are at the moment preparing a spin-off, but there's also recent spin-off, and I would emphasize this thermologics. This is connected to ARPAS, the new principle of a detector, which has been that was the idea of Sergei Borisenko, as mentioned here. He has then developed, wrote this patent and developed this prototype back in 2018, 2019. There was also some support coming directly from IFW and also from funding organizations. And then now, 4 years ago, he founds a startup company, this Thermologics, this new detector, which allows to Fermi surface mapping. I don't know whether Sergei will describe in more detail about that, but at least this machine is also crucial for our joint activity. And that's a very nice example that you really come from fundamental science, from fundamental spectroscopy, to even to spin-off companies. So fundamental science, nice publications, applications. We have a lot of international corporations also. And this is a list of cooperation partners which I usually show. You see several of them are in Italy. We have close cooperation people in India as well, and in Calcutta, Amsterdam, in Grenoble, also in France. We are setting up something very close with Czech at the moment, nearby. But a very, very important aspect here is also our joint activity with Ukraine, which I will describe in more detail in the next minutes. Maybe I should also mention that the IFW is the best ranked Leibniz Institute in the Humboldt ranking. So that means a lot of foreigners come here and get funding then from the Humboldt Foundation to stay here for 1 or 2 years and then go back to their country typically. And then the Humboldt Foundation even gives a chance that then postdocs from Germany can come to the place where the former Humboldt fellow is now working. So we have a lot of successful applications in this Humboldt Foundation. We have Humboldt prizes, fellowships, partnerships. Also, we have also Humboldt partnership. Actually, with Kyiv, we have a Humboldt partnership is also ongoing. So that when we have a look on the ongoing cooperation with Ukraine at the moment, so we have several projects, and they also cover a broad range of activities. You see, we also have nice activities on machine learning for additive manufacturing, which brings together, let's say, theoretical physics or computer physics, let's call it like that, and this really very applied material science. Okay, this doesn't work. Sorry, I'm trying to. Yeah, okay, good. Links together theory and theory and material science. We have since various years an institute's partnership where we work on van der Waals materials. You saw how relevant this is, and we study emergent superconductivity in van der Waals semimetals. That's with Kyiv. At the moment, we have 5 fellows paid by the Philipp Schwarz Initiative for scientists at risk. So there's still a chance to get particular funding for Ukrainians here in Germany. We have ongoing funding from the European Union, also a fellow for Ukrainian scientists from TU Dresden. We have a fellow, and there are also a lot of Ukrainian people now integrated in DFG research projects. Actually, there is a chance to get funding from the DFG to pay people in the Ukraine. We are currently waiting for the result of such proposals, which we have submitted. But there's already ongoing research in this direction. I should also emphasize the success story. Sasha already mentioned this UKATOP project. It was funded between 2018 and 2023. So that was dealing with topological order of electrons. That was the interaction of these 3 institutions. So IFW together with TU Dresden here, and then these 2 institutions in Kyiv. You can also have a look on the homepage. I think there are a lot of giant people. That was really, for us, it was really a big success story. Great thing. Now let's move on to this, to the topic of this new project. So German-Ukrainian Research Center for Quantum Materials. What we are doing there is, again, research, education, and innovation. We have a QMatS team here in Dresden, and we have a Leibniz lab in Kyiv. Project start is just last month, so June 24th. It's for 4 years, and there's a substantial funding. So if you compare the numbers in the beginning, so we have about 10 million per year. So here it's whatever, 600,000, 700,000 euros. So it's a really substantial amount of funding also for us. It's a very important project also concerning funding. It gives us a lot of options to do something. Let's start with the joint Leibniz lab in Kyiv, which we want to set up. We want to improve. The director is Sasha Kortyuk. There are 3 postdocs, 6 PhDs. All of them will have, hopefully, the chance to have research stays at the IFW funded by the project. We also try to develop scientific infrastructure in Kyiv directly. There are some examples of machines which have already been transferred to Kyiv. There's a crystal is a floating zone furnace, optical floating zone furnace, which allows traveling solvent flux melting, growth of oxides and other materials here. We have a magnetocryostat, which has been transferred. We will transfer soon a multi-target sputtering machine, a sputtering system, which will be transferred in the next weeks or months. And then within the project, we will set up mini ARPAs where this detector, which has been developed by Sergei Borisenko and which is now sold by Fermiologics, will be a main aspect. And we hope to set up these mini ARPAs, and then it will be transferred hopefully next year. So this is the joint lab. The research is dealing then with novel quantum materials, optimization of materials, interfaces for potential applications, and quantum devices. You see, these words are very similar to that, what you heard about our main activities as the IFW. So this is really research which is in the core of our interest. We will have this combined multidisciplinary approach, bringing together theory, synthesis, and experiment. So it's also very nicely fitting to IFW's activities. And then new aspects are this artificial intelligence assisted materials design. And this will rely to a large amount on these novel ultra-fast Fermi surface mapping. So this new detector, which will be then the main part of this new mini ARPA system. So this research and education. So within this project, we will have also a chance to establish a sustainable research education system that helps to convert brain drain into brain circulation. That's our hope, that people really go from one side to the other and circulate, and that there will be a really nice exchange. So there will be an option for all students to come to us. There will be a student training at the Leibniz Lab in Kyiv. There will be a student exchange program, bringing students for some time to Dresden. For example, we will have 1 semester research stays at the IFW for master students. And what we also want to establish now are so-called binational doctorates, so that the PhD degree is valid at both places, in Kyiv and in Dresden. And this we did already with France. We establish it also with universities in Italy, and I hope we can also be a substantial important part of our educational project part within QMatS. The innovation part is also important. So we want to promote the knowledge and technology transfer between the institutions and try to create an innovation network, including also innovation-oriented education, of course, but also try to foster activities towards spin-offs or startups or spin-offs. And of course, Fermiologics are mentioned here, but also this academic city, which is an aspect in Kyiv, which could be very important in this respect. So there are a lot of opportunities for young people here at the IFW. You can work in exciting current scientific topics with state-of-the-art facilities. You can come here for short research stays. You can apply for PhD, for binational PhDs. You can apply for scholarships with other facilities, with other organizations. So there will be strong support from our side, and everybody is welcome if you're interested to come here during this project. Or besides that, and if you want to learn more on our institute, you can look at our homepage, in particular on the IFF. This is the Institute on Condensed Matter Physics, where I'm responsible for. If you want to learn something about theory, then you can go to this homepage. And if you want to learn something about our joint project and the progress, you can go to this homepage, which will be available soon, now or later. So this is what I want to say. So thank you very much for your attention.
Thank you, Bernd, very much for a very informative talk and for very informative presentation. Please, questions. In Kyiv, no alarm, but I think I hope all the people are sitting in safe place. For here, you can go to shelter. Actually, if you go to shelter, people don't. So okay, but we do not have too many people. Okay, so questions, please.
Hi.
Alexey, yeah, please.
Hi, I have a question. Can I ask?
Yeah.
Please.
Yes. I hear you speak about oriented crystals. Can you please explain technology of their growing? How orientation is directed by which influence of which?
Okay, so when we discuss our synthesis activities, we have a broad range of methods. So one aspect is this flux growth, or also optical floating zone of large single crystals. In flux growth, at the end of the day, you follow a procedure, then you cool down the flux, and then you sort out to look for the crystals, and then you have, let's say, hope that crystals grow, and then you have to orient them later on by X-ray diffraction. In the case of this traveling solvent flux melting, so this floating zone thing, you sometimes start with a seed crystal, and then the orientation is given already a bit, but also there, it depends on the material, on the properties, how the materials grow and how single crystals grow. But there are other techniques. For example, if you look at all these van der Waals materials, where you have these clear two-dimensional structures, they are often grown by so-called CVT or CVD, so chemical vapor transport or chemical vapor deposition techniques. And there you start from some kind of gas phase, and you have a transfer in the gas phase to a substrate, and then these materials grow on the substrate. And then let's say the challenge is to get either large crystals or you want to have ultra thin crystals. Sometimes we grow very thin, small crystals, which we then use for transport measurements, or we even grow heterostructures. So we start from one material, and then on top of that, we grow different materials. So this is CVD grown, or for 2D crystals. You can even go a step further. So our chemist colleague is working on so-called ALD. There, she's working with monolayers of materials, and then the chemical reaction takes place on the substrate. And this is very important for all kinds of applications. If you want to make devices, then you put in, via the gas phase, you put in molecules on some kind of material, and then you make this chemical reaction to get a monolayer of a material. And this, and Anjana, she's really expert. She can do that with very different materials. Often it's not monocrystalline, but in best cases, even a single crystal. And then, of course, we have the other techniques, as MBE or PLD, where you grow thin films layer by layer, in best case for MBE. So there's a broad spectrum of different things. If you need huge crystals for neutron scattering, you have to do it with this floating zone machines. If you need nanocrystals for transport, often CVD or CVT is the right thing to do.
May I ask?
Okay, sorry, my microphone was switched off. Please, Kirill, if you have questions, raise a hand or just switch on microphone and proceed.
Yeah, on the slide, you explained research by Joint Center QMatS. There's lens layer, but we in Ukraine have no facilities to produce 3D lenses. I'm now ordering if I need from Delft or other universities. So does Leibniz Institute Dresden or TU Dresden has such facilities to produce custom lenses for these experiments?
This I don't know really. So on the QMatS research, I showed this detector with the lens, which has been developed by Sergey. Okay, this is the idea of Sergey, and this is now built up by the company Fisuma here at the IFW. No, Sergey, maybe you can help me at that point. In principle, we have, of course, a workshop here. We have electrical workshop here. We have mechanical workshop. We can do a lot. But this depends. I would say the answer to you depends on the question, what you would like to do. Yeah.
Were you interested in optical lenses or electronic lenses?
Optical. I'm head of photonics cluster.
Okay.
So it's electronic lens, yeah, not optical.
On the figure, that was an electronic lens. No.
Okay.
We are not, so in our research, optical lenses do not play a crucial role. Let's call it like that. I think that's fair to say. Yeah.
Okay, thank you. It's clear.
We buy them too.
We buy them. We certainly
okay.
buy them. And maybe if there is a concrete interest in having something, we should discuss this. And I don't know, I cannot promise this story, but typically one finds a way if it is necessary. If there are some special things we could do here, but we are not experts in optical lenses.
Thank you. It's clear. And second question, you mentioned artificial intelligent assistance research. And do you use quantum computing and quantum modeling for research of materials properties?
So this I transfer to Jeroen. So he's a theoretician and he can tell you what we are doing with artificial intelligence. I only have a natural intelligence, and even this is limited.
Yeah. Well, also that's the only thing I have, and it's also limited. But yeah, what we do with machine learning techniques is more or less standard approaches. We apply them to typically high throughput. Well, there are different directions, but one of them is doing high throughput calculations on materials to either screen for materials with interesting properties or design materials with interesting properties. So we are working on quantum materials, so materials with quantum properties, but we're not using quantum computers to do machine learning, which is, in itself a very exciting and I would say mathematical or informatics topic, but that's not our not something we do. Another direction that Bernd mentioned is the control of very complex manufacturing processes. So, for instance, this additive manufacturing, where you, with a laser, melt a material or powder in a bed, and then in that way make 3D printing of metals, which is a very complicated process, which you want to kind of feedback in real time. So you're observing some quantities, and then you want to feedback in real time to adjust the process. And this also requires some very smart informatics solutions which are related to pattern recognition and machine learning. So these are just two examples of things that we are interested in and doing.
Thank you. Actually, we have in Lviv enterprise who made nano printing, nanoscale additive printing with different materials called Novi Nano. So
yeah,
okay, it's interesting. Okay,
but maybe that would be interesting really to team up in some way. That's
we have a project with Kyiv, with the Franchevich Institute, but that would be interesting. And I'll write you an email about it later.
Yeah, and maybe
I'll connect you.
Yeah, because there are other options to try to get some funding, some joint projects. So let's say the DFG, which I've mentioned, offers a possibility to transfer money from Germany to Ukraine. At least formally, it seems to be possible. We'll see how it works. So that means that could be a short notice way to get funding for such dedicated projects if there is a joint research interest. Yeah. Going beyond, okay, we can team up with our QMatS, but we can also do on top of that such individual small projects if you want.
Thank you.
Okay, thank you. I see that Alexei still have raised hand. Alexei, do you have a question?
I have additional questions. Do you have experience with orientation of liquid crystals by surfaces or etc.?
Oh man, I think we do not have real experience on that, liquid crystals. So it's not a topic where we are good. So maybe I should not promise too much. No, I think let's say Axel is not here with the STEM guy, and he has a lot of things what he can do and a lot of ideas what he can do. And if someone could work in this direction, then Axel could try to look whether, I don't know whether TEM is able to help at that point. I don't know, but we have no experience in this direction. No.
Okay, if there is no more questions, then thank you, Bernd, again for very nice presentation. And we switch to another case